In this video, we move on to section 5.6, which will be discussing the ratio test. And so what the ratio test says is if you're given a series, write the sum from 1 to infinity of an that has non-zero terms. So none of the terms could be 0. And then we're going to define this thing, which I'm going to call rho, which rho is a Greek letter R. And that stands for, excuse me, the ratio. So what we're finding really when you look at this notation, we're going to do the formula for an plus 1 over the formula for an. And what that is, remember, an plus 1 is the term after an. So we're looking at what's happening between to the ratio between two consecutive terms as, right, we go far down the series, right? And so why do we care about that is because we want to know, are we going to keep, is it changing a lot, right? Like, are we going to continue growing or not, right? And so we see that if the ratio is very small, right, if the ratio rho is between 0 and 1, then we get that the series converges absolutely. And then 2, if the ratio is bigger than 1, or if the ratio is infinite, then obviously we're going to have to converge, right? Because we're talking about the ratio between two terms, right? And so then if it's equal to 1, then we're not sure, right? Because it could converge, right, to one specific real number, but the test doesn't tell us that. Oh, I meant the test is inconclusive. Okay, and when is this handy, right? So at the beginning of this chapter, I talked about factorials and exponential functions, and I went over what a factorial is, and this is where it's going to come to play. And this ratio test is going to be very important when we go to the next chapter, in chapter 6, and talk about power series. So it's particularly useful for series whose terms contain factorials or exponentials. Okay, so let's do some examples. So hopefully this makes sense. So for all of these, we're going to use the ratio test in order to determine whether the series converges or diverges. And so let's do this. Okay, so the first one is the sum from 1 to infinity of 2 to the n, that's an exponential, over n factorial, which is a factorial, right? So this is a good series to do the test on, right? So what's an, right? An, remember, is just the sequence that the series is built off of. So we're given that formula, and then an plus 1, what's happening, right? We're just replacing all of the n's now with n plus 1. So let's do that. So an plus 1 is 2 to the n plus 1 all over n plus 1 factorial. So now let's derive our rho, which the formula was the limit as n approaches infinity of the absolute value of an plus 1 divided by an, right? So now let's plug in our an plus 1 and our an. So that's 2 to the n plus 1 all over n plus 1 factorial all over 2 to the n over n factorial. And right, so this inevitably is always going to give us, right, if our series has a fraction in it, then it's going to be a fraction divided by a fraction, which we can't do. So we need to instead multiply by the reciprocal of the denominator. So I'm going to flip that denominator. It's going to become n factorial over 2n. Right, and so, oops, I dropped my limit when I brought this down. So let me just add my limit in there because that's coming along for the ride. Right, and then when we look at this, right, so let's think about what's actually going on here, right? And what I'm going to do is I'm going to rewrite this, right? Because I know that this is all, right? This is all basically one fraction because it's all just multiplied together. Remember, for fractions, you just multiply across. But I want to organize to put, right, the factorial over the factorial and then the exponential over the exponential. So that way I can have things cancel out. Right, so this is going to become the absolute value of 2 to the n plus 1, and I'm going to put the 2n on this side, times n factorial over n plus 1 factorial, right? So it doesn't matter the order that you multiply in, right? And then notice, right, so when I'm looking at 2n plus 1, right, you have to notice what is that, right? Because remember that the rule for exponents is that if you have something raised to some power times that same thing raised to another power, then what do? You add the powers. So I can split up this sum as 2 to the n times 2 to the 1, right, which is just 2n to the 2. Right, and same thing with the n plus 1 factorial. What is that? Remember, that's 1 times 2 times 3 times 4 times all the way down until we multiply by n plus 1, right? The face of our factorial is the last term in our product, but before that term we also have n right before it, right? N is the term right before n plus 1, right? And then n minus 1 is the term before that, and then n minus 2 would be before that, n minus 3, right? But that's overkill, so we'll stop right there, right? So what do you notice? What you should notice is that, right, these first n terms, right, that's actually n factorial. So what you have to notice is that n plus 1 factorial is n factorial times n plus 1. Right, so we can use this here to rewrite our 2n plus 1, and we can use this here to rewrite our n plus 1 factorial. So we're going to plug those things into our row, right? So remember, we're trying to calculate row right now. So 2 to the n plus 1, that's really just 2 to the n times 2 all over 2 to the n times n factorial divided by n factorial times n plus 1. Right, and if I'm doing 2 to the n times 2, but I'm going to divide by the 2 to the n, then there was no point in me multiplying by it, right? Same thing with the n factorial, so those divide out. And then we get the limit as n approaches infinity of 2 over n plus 1 is all we have left. Right, and we really don't even need these absolute value signs because 2 is positive and n plus 1 is positive. Right, so we see that this limit is just 0 because n is in the denominator. So rho is 0, so that meets the first criteria, and so we get that it converges absolutely. So therefore, since rho was between 0 and 1, we know that the series, the sum from 1 to infinity of 2 to the n over n factorial converges. We weren't even asked, does it converge? Absolutely, right, by the ratio test. Okay, and let's do another example or two. Right, so in this example, we're given the sum from 1 to infinity of n to the n over n factorial. Right, so we know that that's our a, and what's given to us is the formula in the series. And then I gotta plug in n plus 1 wherever I see an n into that to get my an plus 1. So that's my an plus 1. So then my formula for rho, remember, is the limit as n approaches infinity of the absolute value of an plus 1 all over an. Right, so that becomes the limit as n approaches infinity of the absolute value of, first we put in our an plus 1, which we got was n plus 1 to the n plus 1 over, oops, this should be n plus 1 factorial. So bad at multitasking, like talking and writing. And that's all over n to the n over n factorial. Right, so then let's rewrite that because we can't divide by a fraction, so we multiply by the reciprocal of the denominator, which means that I just need to flip my denominator, so that's going to become n factorial over n to the n. Right, and then again, right, we know that n plus 1 to the n plus 1, that's just n plus 1 to the n times n plus 1. And then we know that n plus 1 factorial is just n factorial times n plus 1. So the limit becomes the limit as n approaches infinity of the absolute value of n plus 1 to the n times n plus 1 times n factorial all over n factorial times n plus 1 times n to the n. Okay, so now what ends up, did I write all of that down right? Yes. Okay, so now we get that the n factorials are gonna cancel each other out, and then also the n plus 1 is gonna cancel each other out. So then we're left with the limit as n approaches infinity of the absolute value of n plus 1 to the n all over n to the n. So how in the world are we gonna do this limit? Well, notice that they each have the power of n, so we can actually pull that out. Remember, that's one of our exponent rules, so this just becomes n plus 1 all over n to the nth power. Right, and then that's just, right, now we can split this fraction up, and I would get n over n plus, right, so let me write all the steps out. So what I would get is n over n plus 1 over n all to the n. And then I know that this is equals to 1 plus 1 over n to the n. And then what in the world is the limit of that? Right, so then this here is actually equals, right, when we think about this limit here, it's equal to e. And so then since rho is greater than 1, we get that the series actually diverges. Right, that was the second option for rho. Okay,